So let's talk about some of the basics of buoyancy, and I'd like to do this by starting with an example of a helium balloon. Now, buoyancy is a force. There's going to be a buoyant force pushing the balloon up. As the balloon moves up, the balloon has a weight equal to the mass times the acceleration due to gravity, mg, and there's also a force downward on it from air friction. So the buoyant force has to overcome that. But to understand where the buoyant force is actually coming from, let's see some of the concepts of pressure. Now, say for example, I have a solid cylinder that equals that has a mass of 1 kilogram, and the bottom surface area is 10 centimeters squared, and it's on a flat surface here. So we can find the force exerted on the flat surface, which is the weight of it, and that's going to be 9.8 meters per second squared, acceleration due to gravity, and times 1 kilogram, 9.8 newtons. And we're going to change the surface area to meters squared instead of centimeters squared. So we have 10 centimeters squared times 1 meter squared per 10,000 centimeters squared. That's 1 meter squared per 1,000, so it's 1 over 1,000 meters squared. All we have to do to find pressure that I have here, capital P, equals 9.8 newtons divided by 1 over 1,000 meters squared. That's 9,800 newtons per meter squared. That equals 9,800 pascals. Pascal's the unit for pressure. And the reason I'm doing this is to show that the pressure is due to the weight of the mass of the object above it. So we're looking at the pressure at the bottom of the solid on the flat surface. All that pressure, all that force is coming from the force of the weight of the object. So what would happen if this cylinder weren't solid, it were made out of like a liquid? So what would happen is we'd have this cylinder, but then a second later it would just splatter onto the surface and be some kind of puddle. And the reason why that happens and that doesn't happen with a solid is that the solid is all self-contained, so only all the downward weight is shifted downwards onto the surface. But what happens in a fluid like a liquid, or this also happens in a gas, but this example with a liquid, is that the force redistributes itself in all directions. So it's pushing itself out on the sides and it's gonna splatter. But so that means we need to have some kind of container. But the thing about fluids, how they redistribute force in all directions, is what's going to allow the buoyant force to happen, because when we drop something inside the fluid, the pressure is going to push up against the fluid no matter what shape it is, because the pressure is just pushing in all directions. But we'll get to that in a minute. But this, I have this dotted line here. That just means we're going to be measuring the pressure halfway down the fluid. And the thing is, we can't do this with a solid because we can't like stick in our hand and measure the pressure. But if you've ever swam in a pond before, you swim to the bottom. As you get closer to the bottom, you can feel the pressure in your ears getting greater. So you can kind of measure the pressure at different points in the fluid. So if we only go halfway down, that the mass is going to be 0.5 kilogram, because all the pressure comes from the weight above it, not the weight below it here. And so if we want to measure the downward pressure on, say, a disc here at the dotted line, we're just taking half the mass, same surface area, and we're going to go through the same process as we did earlier, except now it's going to be half the force, and the pressure is going to be the same surface area, half the force. We're going to have half the pressure. We have 4,900 pascals. Up here we had 9,800. So that's important. But then also, since pressure, the force in a fluid distributes itself in all directions, the total pressure and total force on the disc here is going to be 0, because the pressure from the top that we just measured is 4,900 pascals. But the thing is, like just below the disc, infinitely small distance below the disc, we're going to have the same pressure going up, because the pressure is the same at the same point and it's going to be pushing in all directions, so it's pushing up, and forces from the sides cancel each other out. And it has to equal 0, because if it doesn't equal 0, then the fluid's going to be accelerating up or down, and the fluid's just standing still in this case. And we can use this in a minute, but if I give you the height of the cylinder, which I haven't given you yet, say it's 7 centimeters, we can find the volume, and from the volume we can find the density, and that's going to be important. So the volume is surface area times height. 10 centimeters squared is the surface area of the base, sorry. But 10 centimeters squared times 7 centimeters height is 70 centimeters cubed. The mass equals the volume times this little Greek letter here, rho, which signifies density. So rho, or the density, equals mass over volume. The mass is 1 kilogram divided by 70 centimeters cubed is 1,000 grams over 70 centimeters cubed, because in this case I want the density in grams per centimeter cubed. Sometimes you might want it in kilograms per meter cubed, but whatever. So rho is 14.3 grams per centimeters cubed, and we're going to use that in a minute. But just to understand here, say I want to drop a cube inside a fluid. There's going to be forces on the sides of the cube. Those are going to cancel each other out, so we're not really concerned about them. But the thing is here, as I showed earlier, when we go down to the bottom of the cylinder versus in the middle of the cylinder, the bottom of the cylinder, the pressure is higher. So the pressure is higher at lower points because there's more mass of fluid above it. So this arrow pushing up is going to be greater than the arrow pushing down. And then there's another arrow pushing down of the weight of the cube. So if the difference between this pushing down and this pushing up is greater than the weight, it'll float, because this will overcome the weight and push it up. But if not, then it will sink, but it's also lower. The weight will also be lower. But so say I want to draw an imaginary cube inside a fluid, and say the cube is full of the same fluid. There's going to be a force equal to the pressure on the top times the surface area plus the weight, and that's all the force that's going to push down. And then there's going to be a pressure on the bottom times the surface area. That's the force pushing up. And that has to equal 0, because since we're just drawing an imaginary cube at this point, that cube is made of the same material as the medium. So the force has to equal 0 because the fluid's not moving around within itself. So that can be rewritten as the force on the top plus the force of gravity, and the positive force is pushing down, and then minus the force on the bottom, the negative force is pushing up. That has to equal 0, but this signifies fake cube, massive fake cube. But the mass of the fake cube equals the volume of the cube times rho, and we found rho on the previous page to be 14.3 grams per centimeter cubed. So since mass is volume times rho and the volume stays the same, if the density is lower, the mass is going to be lower, and that means this whole side of it, since we're adding it, this whole side of the equation is going to be lower, and therefore the net force is actually going to be less than 0. So if the density is less than the density of the medium, the force is going to push up, because we already put the negative forces as up and positive forces down. But if the density is greater, this whole side of the equation is going to be bigger, and that means it's going to be bigger than 0, and it'll sink because there's going to be a positive net force on it, and we showed positive forces pushing down. And it doesn't matter the shape. If you can try it with different shapes, and can say there's forces at these different interfaces. This shape's a little easier than, say, this irregular shape here. But it doesn't matter the shape. There's always force pushing down and pushing up. And since everything has some kind of thickness, the force on the bottom is greater than the force on the top. And that brings us to the Archimedes principle that the force of buoyancy equals the weight of the displaced